So I want to thank everybody that is here and also on Zoom. And today we have the pleasure to be hosting this joint seminar with the IMA, which the Scottish Branch, I think it is. And today we have the honor of having Pablo Padilla, Professor Pablo Padilla, which at the moment he's researcher at the Institute of Applied Mathematics. I will say what in English should be. And he's also professor of the School of Music. They are in the National Autonomous of Mexico. So this is not normal, I think. And today, Pablo is going to speak about Hopf bifurcation for a fractional van der Pol oscillator. And he will talk about application on to aerodynamics and some implications to Flutter. So Pablo, thank you very much for accepting, and please be my guest.
Well, no, the other way around. Thank you for the invitation, and I hope we can discuss things later.
Yeah.
So let me start by reading the title of the talk: Hopf bifurcation for a fractional van der Pol oscillator, applications to aerodynamics and implications in Flutter. So I will start by showing you a movie, because I would like to eventually get more formal and say what Flutter is, but I think that a picture says more than 1,000 words. So let me. What you will see in this movie is what's happening with the airfoil in the back part of the plane, and an experimental setting trying to mimic that.
Pablo, you trying to show a movie? I'm not sure a movie's showing.
Yeah, Pablo, we are just seeing the presentation, but the first slide.
Oh, don't tell me that.
We can see only the first slide. Do you want to stop sharing and sharing again?
Yes.
Okay, yeah, try again.
Okay, I see your mouse now, so yeah, now it's working.
Now it's working.
And now you see the picture of the back part of the plane, and I hope it moves eventually. So is it possible to see it now? The oscillation going on the back part of the plane and the airfoil.
Yes,
the small wing, the back wing of the plane, and the corresponding experimental setting. So this is fluttering. Fluttering is an oscillation caused by a fluid interacting with a solid structure. I will be more accurate about that, but let me show you why it is important. And several instances and cases of fluttering. So this is another example in which a system, a solid system, elastic in this case, starts oscillating because of the interaction with the fluid. And I'll show you two more videos, which I hope illustrate why it is important to understand how Flutter arises and the onset of the whole process. This is a wind tunnel with an airfoil inside it, and wind velocity which is being increased from very low values to larger and larger values, and see what happens. And let me show you a very famous example, which now is understood in terms of fluttering. This is the Tacoma Bridge, already many years ago, but it starts oscillating very heavily until it collapses. So having shown the videos, let me go back to the boring part of the presentation and try to give at least an operational definition of what Flutter is. So Flutter is a self-excited oscillation, as it says here, caused by interaction between a fluid and a solid. And I will distinguish, in the literature, there are two distinctions, two kinds of flutter. What is called classical flutter, which is due to the fact that the incoming fluid has a very large velocity. So the magnitude of the velocity of the free stream velocity is very large, and the solid structure starts oscillating. And the problem is that these oscillations might end up in collapse many times. That's one of the important implications of fluttering. The other is called stall flutter, which is due to flow separation. What happens is that the free stream velocity starts increasing from small values, and as with some of the examples we saw, in fact, as with the Tacoma Bridge example, and then the flow becomes non-stationary. So in particular, we have, for instance, vortices or periodic structures that start interacting with the solid structure, and they resonate. So a stall flutter can be thought of some sort of resonance phenomenon in which the fluid starts moving periodically and forcing the solid structure. Oh, by the way, I didn't mention, but in case something is not clear, you want to ask a question just to clarify things, please feel free to interrupt and ask. So here comes the math, and I would like to be very sketchy about the way we do it, but I would like to mention a few important facts about fractional calculus and the way in which it enters elasticity theory and elastic models. First of all, I would like to say a few words about the history of calculus, the fractional calculus, which is kind of fashionable nowadays, but it's got a long history. It goes back at least to Leibniz and L'Hopital. There's a by now famous letter between Leibniz and L'Hopital, in which one of them, I think it is Leibniz who asks L'Hopital if there's any meaning in trying to compute derivatives of non-integer values. So not to compute the first or the second or the third derivative, but to compute half a derivative of a function. And the only reply he gets from L'Hopital is that it is indeed a very deep question, and that he's sure that it will have important applications if it is eventually found out how that is done. Many people worked on the subject. At least I should mention two of them in the classical history of the fractional calculus, which are the founders of the field somehow, Riemann and Liouville. And in fact, there's one way of defining the fractional derivative, which is precisely the Riemann-Liouville derivative, which will not be using, we will be using another definition for technical reasons, which I won't go into, which is called the Caputo derivative. Caputo is an Italian mathematician already in the 20th century, not that long ago actually, who introduced a modification of the fractional derivative for technical purposes, as I said earlier. But anyway, having said a little bit about the history of fractional calculus, I would like to say that it's turned out to be useful in modeling several problems, several natural processes. In particular, it's been, and in part, it appeared for the first time trying to understand anomalous diffusion. So in diffusion processes which are not standard Gaussian processes. So for instance, in trying to write down the corresponding Fokker-Planck equation for a Levy process, or diffusions which are faster, what are called super diffusions or subdiffusions. If one tries to write down the corresponding heat equation for the Gaussian case, one ends up with a fractional operator. In elasticity and other fields, they have found important applications, and even in fields like mathematical finance, for instance. And why is that? I guess the reason is that as opposed to integer derivatives, fractional derivatives are represented by integral operators, which seems a little bit odd to represent derivatives as integrals, but that's the way it works. And they have a intrinsic non-local character, and this non-locality is useful in incorporating memory effects and another in time or another or non-local aspects of some physical processes. So as a preamble for fractional calculus, I think I finished with that. Everything was said in order to justify what I'm going to do right now. And the justification is that in the usual derivations of the equations for elasticity theory, we will replace the standard time derivative with a fractional derivative. You would ask why we do that, and my plain answer will be because it works sometimes. So instead of taking the stress tensor as defined in the classical case by the Lamé parameters and the standard relation, we take more a viscoelastic or fluid representation of the tensor and replace the material derivative with the material derivative in which there is a fractional derivative. So it is pretty straightforward. And before I take, sorry?
Cover the original documents పెట్టాను ఇచ్చావా నా మాయాలకి
దేనికి
ఆరెంజ్ కలర్ కవర్ లోని ప్రాపర్టీ ఒరిజినల్ డాక్యుమెంట్స్ పెట్టాను
Sorry, I'm listening to something.
There is no interference here, or
Excuse me. If anybody is not muted, please do so unless you're asking a question. Particularly, I think it's somebody called Yogesh who is broadcasting at the moment. Thank you.
okay, it's already done. Thank you.
So Pablo, if I could, I'll sort of interject a question since we had a small interruption there. So could
Sure.
Could you clarify the meaning of this symbol I-T to the 1 minus alpha? Is that an integral operator?
It's an integral operator, and that the integral operator, the integral fractional operator of order 1 minus alpha.
Yeah.
And now that you ask, it's probably a good point to clarify that in order to define fractional derivatives, the standard approach is to define first fractional integrals, and fractional derivatives are considered fractional integrals of negative order. So at least that's something that comes out of the theory, which is very nice. I think this sort of equivalence or uniformity in dealing with integrals and derivatives. But indeed, the I sub t is an integral operator, which by definition is non-local.
Yeah. So is it fair to say then that what you've got there, if I could, is you're interpolating between the first derivative and pure convection? As alpha varies from 1 to 0.
Physically, that's one way of looking at that. At least in the mathematical model, what happens in practice, I still don't know. I think my feeling is that in terms of convection and diffusion, if you have a process which is non-Gaussian, you can sometimes, as what happens with the porous medium equation, for instance, in which you can decompose the effect in diffusion and convection. But there is something I wouldn't like to get much into, because I don't know the real answer. that's the truth. But anyway, resuming what I was saying, I just pointed out the fact that we take a stress tensor which is more of the fluid type, in which the material derivative has been replaced by a fractional material derivative. And then there are some computations in order to justify a derivation from an extended parameter formulation, a concentrated parameter version. So let me say what the end result of this process will be. We will end up with a fractional van der Pol equation. And there are still many gaps to be filled. This is some sort of a hand-waving justification of a fractional van der Pol model for fluttering. We take the left-hand side of the stress tensor and apply some sort of mean value theorem for integrals and get this equation. And the same thing with the right-hand side with the new stress tensor, in which the fractional derivative appears. I will be very sketchy here, because what we end up, broadly speaking, is with an ODE, which describes an oscillatory system in which the forcing, well, the right-hand side has some sort of fractional dependence in the derivative of the position. So in several papers, both old and new, in particular, it's not a typo. I was going to say I have two references here, one to Minorski in 1947 and the other to Minorski 2009. They also justify approaching fluttering via a van der Pol equation. So if one considers carefully the van der Pol equation, and we could have probably started more directly from that, I would just wanted to give at least a partial justification of how we arrived at this equation from first principles. although not in a rigorous way. What we end up with is a van der Pol oscillation, in which you have basically a harmonic oscillator with a nonlinear term corresponding to dissipation. And the idea is that dissipative processes, which are usually modeled by integer derivatives, could be better modeled, or could fit experimental data better if one introduces fractional derivatives. So summing up, our model reduces to a van der Pol equation. Let me show you which one it is. It is this one, in which the dissipation term, which is usually considered to be proportional to the first derivative, is now proportional to a fractional derivative. And I already mentioned that we chose the Caputo derivative for technical reasons. I guess I should just clarify this point. Surprisingly enough, if one takes some of the definitions of fractional derivatives, like the Riemann-Liouville definition, it is not true that the derivative of a constant is zero, whereas it is true for the Caputo derivative. And so it turns out that in practical terms, for many applications of initial value problems, using the Caputo derivative is more practical, except for a correcting term, they coincide. But going back to the description of the model, what I will be talking about from now on is of this van der Pol modified model with a fractional derivative for the dissipative term, and what we call a fractional van der Pol equation. I think that even just from the mathematical perspective, it is interesting in itself. And there are some papers already about bifurcation in fractional systems, and I'll be using some of the results by other authors. But I would like to point out that standard problems or standard questions in dynamical systems and differential equations become interesting, both from the perspective of applications and from the theoretical perspective, when one considers fractional operators. I'm thinking, for instance, of bifurcation analysis in general. I'm thinking about control theory or control theoretical approaches to dynamical systems, in which introducing fractional operators adds to the complexity, both mathematical and modeling complexity. So what I would like to stress is the fact that even if they are fashionable, it's or that I believe to some extent they are fashionable for a good reason, and there are genuine mathematical and physical problems to be understood related to fractional derivatives, particularly in which non-local terms or non-local effects want to be incorporated. So let me say a few words about the standard treatment of the equation, which is a second order fractional equation. So what we do here is the standard trick of introducing additional variables in order to reduce the order of the system, in which in this case, since it is a fractional order system, we cannot write it as a first order system, but we introduce y and z as additional variables to write the system as a system which contains the derivatives of order no higher than 1. This is for technical reasons and because we want to apply some bifurcation and stability results which apply precisely for this case. So we end up with a system of three equations. The fractional derivative of order alpha with respect to t of y, of x equals y, the derivative of y with respect to t equals z, and the original one describing the dynamics. We might write down in matrix notation in this way, where the script d alpha is a vector fractional differential operator, and b is a matrix that incorporates the linear and nonlinear terms. So to be more explicit, b is this, and what we'll be considering now is the standard linearization process in order to study bifurcation when mu is a bifurcation parameter and it varies from negative to positive values. So let me go back to the original van der Pol equation. The classical van der Pol equation is known to have a Hopf bifurcation for mu equals 0. So notice the change of sign here. I have a minus mu with the standard plus sign. The usual loss on instability implies that the origin, which is an equilibrium point, becomes unstable, and a limit cycle appears as soon as mu is positive. So we'll be trying to discuss the connection with Flutter later on, but if we accept that our model is given by this fractional van der Pol equation, this is what we have to understand. Basically, what I'll be discussing now are the conditions on the linearization, so that for the fractional case, there's also a Hopf bifurcation, and I would have to make a few comments about the result, but let me just present the result, which is due to Daly and Liu. And of course reduces to the classical bifurcation result when the orders of differentiation are integers. But the point I want to clarify is that this result is for orders of differentiation which are rational, which seems a little bit odd. There are extensions to general irrational fractional orders, but they become technically more involved. And since for applications in terms of fitting curves with a certain power behavior, we will use rational approximations anyway. We are not bothered by the limitation of the theorem. So let me try to explain to you more or less what the meaning of the theorem is, and to check at least that it reduces to the classical bifurcation result. If I may remind you of what the mechanism of Hopf bifurcation is, for the linearization of the equation, one has a pair of eigenvalues that have real part negative, but as the bifurcation parameter increases, this pair of complex conjugate eigenvalues crosses the imaginary axis, and then the real part of the roots become positive, and that's what causes the instability of the origin and the formation of the limit cycle. So one has to consider the generalized characteristic polynomial, which is this here, and here we are assuming that alpha can be represented as a rational number P over Q, and that Q is the common denominator of, in our case, degrees of differentiation, 1 alpha and 1 minus alpha. So the result looks pretty much the same. So if this generalized characteristic polynomial, if that has negative real parts, then the zero solution of the system is asymptotically stable, where alpha I is real and lies in 0, 1. So for that matter, the result is pretty much the same, except that the computation of the characteristic polynomial varies a little bit. So the characteristic polynomial in the fractional case, it is this one here. I hope you can see my pointer, my mouse. So
Yes,
what
we
you
can.
have, sorry, you can see it?
We can see the pointer of the mouse.
Okay. So basically, from a technical perspective, it is a matter of computing the right characteristic polynomial, which is a generalized characteristic polynomial, modified by the fact that we have fractional derivatives, and which reduces to what I denote here by P of lambda. And the instability condition happens with when the again when a pair of eigenvalues crosses the imaginary part, but because of the modification, there are things that change, and in fact, the condition is that there are two lines defined by the angle pi over 2k over 2q, and if the argument of one of the roots of the generalized characteristic polynomials is bigger than this angle, then the system becomes unstable. So if we are talking about integer derivatives, the classical case, q is always 1, and the condition reduces to the standard condition that the angle or the argument of the roots has to be bigger than pi over 2, so has to cross the imaginary axis transversally. In this case, this is only possible when mu equals 0, and what we are saying is that for the fractional system, for the fractional model, there's also a Hopf bifurcation, but it occurs precisely at the same value, at the same bifurcating parameter value of mu equals 0, which is, if you want, a little bit disappointing, because what we expected at the beginning of our project was to be able to prove that considering fractional derivative effects actually moved the value of the bifurcation point so that a system might become unstable before by the introduction of by the consideration of these non-local effects. In fact, at least in this concentrated parameter model, that doesn't happen. The value of the bifurcating parameter, bifurcation parameter, is also 0, and this is numerically shown in this picture. What you see in this picture is the value of the maximum argument of the polynomial, of the characteristic polynomial of the equation for different values of alpha. So the case alpha equals 1, which is the sort of bluish line, corresponds to the classical case. And you see, and the red line, the horizontal red line, corresponds to pi over 2, which is the instability threshold. So you can see that no matter what value of the differentiation order you take, alpha equals 0.8, alpha equals 0.5, and so on, the crossing stability line is at the same point, which is mu equals 0. But something which will be important, and that's something which we realized afterwards, is the slope with which the different lines cross the instability point, the instability threshold, is different. And that means that the amplitude of the oscillations when bifurcation starts differ depending on what degree of differentiation you have. Let me make a physical observation. Remember that we have a modified van der Pol equation and that we had dissipation corresponding to the fractional derivative of order alpha. So what we are saying is that the bigger the alpha, the higher the dissipation, and this is shown in the plots for the actual solutions. So you have blue, purple, green, and black in order of increasing degree of differentiation. So you would have higher values of alpha, and therefore, physically speaking, you would have a higher dissipation, and therefore you would expect things to be damped faster, which is actually what is observed in the figure. So at this point, we realize that the effect of precisely introducing fractional effects or non-local effects into the model is not so much to change the threshold of the bifurcation, but to change the way in which the amplitude of the bifurcating periodic solution behaves. And that might have interesting and important applications for fluttering. That might explain why it is still not understood very well, at least the violence of the sudden beginning of oscillations. So what I'm saying is that, to summarize, the degree of differentiation might have to do, or it has to do, with the dampening of the oscillations, and therefore it is interesting and important to consider that from the physical perspective. What you will see here as well, which is basically the same picture, just adding the remark that besides the one I already made about bigger alpha, more dissipation, that there's a small change in the phase, which might have some important implications as well. Here you have pretty much the same representation but in the phase diagram, and you'll see that the smaller the alpha, the longer the time it takes the solution to go to the stable point, spiraling inwards. Whereas for bigger values of alpha, the spiraling process is faster. Oh, just a small comment related to the plotting of the phase diagram. This is, as specified here, the classical, so to speak, phase diagram in which the first derivative is plotted against the state variable. In this one, which is a fractional phase diagram, it is not the first derivative, but the fractional derivative, which is plotted against the state variable, and therefore we have this different way of visualizing. We think that it will be interesting to visualize these phase planes in 3D as a part of a surface, let's say, and try to understand what happens with the variation of alpha, mu, and omega. So finally, I'd like to say a few words about comparison with experimental results, because the justification of the model was somehow heuristic. Nevertheless, there are some comparisons with experiments, and qualitative agreement is good. On the left-hand side, you have an experimental plot of fluttering from 2009 by Dimitriadis and Lee. And on the right-hand side, we have a graph obtained with a van der Pol fractional model for a value of alpha equals 0.5. We are in the process of trying to fit our model with the experimental values of the parameters, but there seems to be some inconsistencies, and we are trying to contact the authors or at least make clear what's going on, because they report a variation of an angular velocity of the order of 10 to the 6, which doesn't seem to be credible. But anyway, this picture and the following one, in which the limit cycle is represented, seem to fit or to agree, at least qualitatively, with our model. So what I'm trying to say is that using a van der Pol, and in our case a fractional van der Pol representation for fluttering, and trying to compare with the experimental data is, I think, not completely meaningless. So to conclude, let me read out what's in the transparency. The current model successfully reproduces the behavior of coupled mechanical systems experiencing flutter, and as I pointed out before, using van der Pol models for fluttering is not new, and it is a fairly reasonable approach. A van der Pol oscillator equation retains the information regarding the first bifurcation presented by these systems. And the fact that the approach used here, which relies on fractional derivatives, encompasses further details regarding the onset of flutter, which we believe deserves to be better understood. In particular, this last remark, specifically how suddenly stability is lost. And what we are trying to do now, and some sort of perspective and future work, we are trying to feed the model with accurate experimental data for the parameters of the system and see if they can actually have some predictive value. Rely on methods such as homogenization to obtain effective parameters for the coupled fluid-solid system, which brings out another question I didn't mention already when I said that bifurcation theory or control theory in the fractional setting might be an interesting point. Here, homogenization problems or some sort of effective medium approach in some fractional systems might be interesting to consider. Also, to extend the current model to include further bifurcation or secondary bifurcations, as they are called technically. And finally, extend the model to a system of two equations to take classical Flutter into account, because this is only referring, the van der Pol model only refers to the second kind of Flutter, which I mentioned in the very beginning of the talk. So it would be interesting to come up with a model for classical fluttering, but and here, not without thanking the invitator thanking the organizer, particularly Ariel, for the invitation, and I guess there's still some time for questions if there are any.
Yeah, thank you very much, Pablo, for this very nice presentation. I hope you hear the sound during this year. So there are questions. In Zoom, Simon raised his hand. So Simon, if you want to.
Yes, so I got a question about your initial equation that you had at one of your slides, where you had the fractional advective time derivative on the left-hand side, and on the right-hand side you had the partial derivative, time derivative. Yeah, this one, number one. So I was wondering about the second term on the right-hand side in equation one. So you have I, so I presume that's the fractional integral in space only, or do you also take into account sorry, time, only time? Yeah,
it's only time.
Okay, so is there any fractional derivatives or integrals in space in your equations?
No, we're
Okay.
working in that, but for the purpose of the informal derivation of the fractional van der Pol equation, we only need the time derivative to modify the material derivative this way. But that's a very interesting question, and that's something we are working on at the moment, because many fractional models have been proposed in elasticity theory, and sometimes they are not even dimensionally consistent.
Right.
The moment you introduce fractional derivatives, you have to take into account some sort of dimensional modification, and some dimensional constants have to appear. That's one thing. And problems like objectivity of the model. So standard things that are taken for granted, that are not immediate or trivial anymore. And so in order to modify the models and the traditional approaches with fractional derivatives, some more care has to be given to these standard derivations.
Okay, thanks.
Thank you very much, Simon. So there are other questions in Zoom or here in the audience. So maybe I just wanted to ask one also in this equation, I was wondering what this notation of the first term on the right-hand side. So I can see the Caputo derivative on the left-hand side, but that partial derivative, if you could explain what it means.
I guess we are using mixed notation. You could represent this as I minus alpha of f.
Okay, so it's okay. Okay, thank you.
I had a question,
I
if I
think
may.
yeah.
So you spoke about the fractional derivative being related to the dissipation in the system. I wonder if you could say anything more about what you mean by varying dissipation in a fluid structure interaction like this.
Sorry, let me try to clarify the question. You would like me to elaborate a little bit on the relationship between the dissipation and fractional derivatives? Or,
yes, please. Yes, in this context.
I would have to talk a little bit about the experimental results in which when you pass to some sort of Fourier representation of the response of the system, there's a response in which a polynomial variation is better to describe the reaction of the system. So if you have a polynomial representation in which the leading power gives you, going back from the Fourier representation, the order of differentiation, you have naturally a model which includes fractional derivatives. So what I'm saying is that from experimental results, you can fit a fractional derivative into the elastic behavior or viscoelastic behavior rather than of the model. And
right. So you're seeing it as arising from viscoelastic
yeah, exactly.
Properties in the solid, in
exactly.
the wing, in other words.
Yeah,
yes.
Yeah, that's precisely the point. If you try to fit the response of a viscoelastic material in the Fourier representation, you end up with a fractional powers of the fit.
I see. And that's why engineers would be interested in tuning this, I guess.
Exactly.
Yeah. Thank you very much.
You're welcome.
I'm sorry? Simon. Simon, did you raise your hand?
Yeah, hi. Yeah, I got a second question. If I may.
Second question, okay. Thank you.
So you have this set of fractional derivatives, a set of ordinary fractional derivatives. Have you solved this explicitly and analytically, or did you look only at the bifurcation properties?
I mean,
yeah, I think we thought it. Okay, so is this actually the solution of the fractional equations?
Exactly, for different degrees of differentiation.
Okay, and what are the solutions made of? Is it of the generalized exponential function? Is it involved?
Well, for the nonlinear fractional van der Pol equation, I don't think that there can be an analytic solution exactly as in the integer case, but for the linearized for the linearized problem, you're right. I mean, it's in terms of generalized exponentials or Mittag-Leffler Mittag-Leffler functions.
Yes. Okay. Okay, thanks.
Thank you very much. So I don't see any hand on Zoom, and I think there are no more questions. So thank you very much, Pablo, again.
Thank you. Thank you for the
Thank you to
invitation.
Nigel and Nick that they helped me for organizing this joint seminar. Okay, so I will stop the recording now, but if people want to stay, I will leave the room open. So, and this time I won't cancel.